Next, we're going to state and prove a theorem that kind of connects uniform continuity with the limit of a function. Theorem 3.5 says that if f, the function f with domain D going into R, is uniformly continuous, and by the definition we're supposed to say on what set, but the book assumes that if you don't say on what set, it just means on the entire domain. So you could put on D there if you'd like to. It's uniformly continuous, uniformly continuous on the entire domain. And x naught is an accumulation point of D, then f has a limit at x naught. So maybe it's been a little bit of time. Let's refresh our memories as to what an accumulation point of D is. X naught does not have to be in the domain. It does not have to be in the set D to be an accumulation point. Every neighborhood, we'll call it an epsilon neighborhood, around x naught must contain an infinite number of points of D in order for it to be an accumulation point. So again, x naught may not be in D, but if we take x for any positive number epsilon, it can be 1 over a trillion, very small, this interval will contain an infinite number of points from the set D. That's the definition of the accumulation point. So, well, what is this really saying? Isn't this true even if it's just a continuous function? And the answer to that is no. Let's take a look at the function f of x equals 1 over x. We just saw that a little bit ago. And let's go from 0 to 1, or actually 0 to anything, 0 to any number. F of x is continuous on, it's actually continuous on its whole domain, which is all real numbers except for the number 0, where it's not defined. Continuous everywhere it's defined. But, well, also, 0 is an accumulation point of the domain. Again, the domain is all real numbers except for 0. So actually that means that every point on the real line is an accumulation point for D. But there is no limit at x naught for two reasons in this function. One of them is because this blows up to infinity as x goes to 0 here, and then it goes down to negative infinity if you approach it from that side. So it's going in two different directions, but basically just the fact that this does not converge, the height of the function does not converge to a real number as x is approaching 0. So if you simply remove the word uniformly, this is not a true statement. Okay, well let's prove this theorem. Proof. All right, so I am trying to prove that there is a limit at x naught. So since there's a limit involved, I need to start off by saying let epsilon greater than 0 be given. And we're going to choose a sequence. Let x in be a sequence in the domain that does not include x0. x0 may or may not be in the domain. That converges to x naught. So I'll say such that x in goes to x naught. Well, since f is uniformly continuous on D, we can let delta greater than 0 be such that the following holds true. And this is going to look just like the definition of uniform continuity. xy in the domain and x minus y less than delta, if all that's true, that implies that f of x minus f of y is less than the value of epsilon. Again, if you want to make a note, we can make this statement, or in other words, such a delta exists because f is uniformly continuous on its entire domain. Since xn converges to x naught, basically just since it's a convergent sequence, we know it's a Cauchy sequence. I'll just write that it's Cauchy. Xn is a Cauchy sequence. We remember now, I'm sure, that in the real numbers, a sequence is convergent if and only if it's a Cauchy sequence. All right, because of that, let capital N be a natural number. Let it be such that, right now we're using the definition of what it means to be a Cauchy sequence. M, little n, greater than or equal to the capital N, implies that xn and xm are very close to each other. In fact, less than delta. I can use any positive number I want there. I chose delta for that one. Okay, since I'm going to repeat myself up here, since f is uniformly continuous, on D, the following holds. I'm going to start off just like this. M and N greater than or equal to capital N implies xn minus xm is less than delta, and I'm just going to continue this a little bit. If you're within delta, right here, that implies this is true. So, f of xn minus f of xm is less than epsilon. And thus, f of xn is a Cauchy sequence. In brackets, I'm going to say, which implies convergent. And that's actually what we were looking for. By theorem 2.1, f has a limit at x naught. And that's the end of the proof.